for each eigenvalue, we are going to have one corresponding eigenvector as well. So what do? We plug in back to these equations here. Says that now we said lambda equals to 5. Yeah, lambda equals to 5. If lambda equals to 5, then this will be minus 1, and this will be minus 2. Okay, and these two column vectors are linearly dependent, right? Because if you put 2 here and put 1 here, then what will I get? I will get plus 1. That will be exactly 0. Okay, so this is one eigenvectors, and then you do the other, do with the other eigenvalue. So we have 5 and 2, right? So you can practice by yourself and plug in 2 and verify what is the vectors over there, eigenvectors over there. This is how you calculate the eigenvalue and eigenvectors. Okay, then is the diagonalizations. So it's not, okay, let's go through the definition. So we say that a square matrix is diagonalizable if that matrix A has distinct linearly independent eigenvectors. Okay, so let's say that if we have then if we have that, then actually we can decompose A into the following way, where all the V here are the eigenvectors of A, and all the lambda is the corresponding eigenvalues. Okay. Okay, so why is that? Suppose that we have any vectors A here. No, not the vector. Any matrix, n by n matrix that has undistinct linearly dependent eigenvectors, and we put them together. So call it P here, and which P is actually V1, V2 linearly independent eigenvectors here. Okay, and according to the definitions, I should put it this way. So we can actually put A inside into each columns here. So what you will get is something like this one. This is column 1. This is column 2. Right? Okay, and according to the definitions of eigenvectors, what we will get is the corresponding corresponding eigenvalues here for each columns, right? 2. This is the nth column, Bn. Okay. And what is this? This is actually, you can write it as PD, which is as the same expression here. The D and D is the matrix here, and P is the like you putting all the eigenvectors together here. Okay, and what is next? You just multiply. Now we know this, and you multiplied P, the inverse of P on both sides, then you will get exactly the expressions you have on the lecture notes. Okay. Right. And why do we need to diagonalize the vectors here? Because once we have it, it's kind of speed up the whole computation process. Speed, I should put it this way, speed. Let's say that we want to calculate something like a to the power of, for example, like q. Oh no, put it 10 to the power of 10. So if we don't have this diagonalized matrix, the only way is like we will do it one by one, right? So for example, like first we calculate this one, and maybe then we do this one, and that will be only like a to the power of 4, right? And you continue to do it, and it is a very tedious process. But if we can diagonalize this this matrix, then what does it look like? So it's like P times D and P minus 1 and to the power of 10. And let's say we only look at the first two cases here. What you will get from here. So these two will cancel out together. And what you will get is P to the D to the power of 2 and P minus 1. Okay. So follow the same arguments. If we want to calculate the power of 10, then what we will get? We will get eventually P times power of 10 and minus 1. This is very easy to calculate because we only have the eigenvalues on the diagonal positions. So that one is very easy to calculate, and hence you can get the result very quick. Right. Okay, so here are some property of it, and right. So if we can diagonalize it, or like A is diagonalizable, then calculate the determinant of A is actually multiplied all the eigenvalue. Okay, and the trace of it is going to be the sum of all the eigenvalue here. Right. Okay. PD here, positive definiteness. So a matrix, a square matrix here, is called symmetries. If once you transpose it, it's still the same. So that is the definitions. And what is positive definiteness here, meaning that if we have a symmetric matrix A over there, and we have a random vectors x in Rn, then if that matrix matrix A satisfied these conditions, meaning that no matter what x you put in here, as long as it's not 0 or 0, then you can get the positive number in the end. Then the matrix A is called positive. How do they call it? Positive definite. Yeah. Right. And if there are some numbers equals 0, then it's semi-definite. And it's all negative, then it's negative definite. Right. Right. And I want to, like with the final minute, 20 minutes, I'm going to talk about the projection matrix here and its relationship with the regressions. Okay. So let's go through the definition first. So this is a projection matrix of X. Okay, it looks this way, and that X has to be full rank, meaning that all columns are linear independent. Okay. And what does this matrix do?